Welcome to this lesson on the electric field due to a short electric dipole. In physics, an electric dipole consists of two equal and opposite charges separated by a small distance. Understanding the electric field created by dipoles is essential for many applications in physics and engineering. Let's first understand what an electric dipole looks like. Here we have two charges, a positive charge plus q and a negative charge minus q, separated by a distance 2a. The dipole moment vector p points from the negative charge to the positive charge and has a magnitude of q times 2a, which is the product of the charge and the separation distance. Note that when we say short electric dipole, we mean that the distance 2a is very small compared to the distance from the dipole to the point where we're calculating the field. Now, let's find the electric field due to this dipole at any point in space. We'll consider two special cases first, points along the axial line and points along the equatorial line. For a point P along the axial line at a distance from the center of the dipole, we can calculate the electric field using Coulomb's law and the principle of superposition. To find the electric field at point P along the axial line, we need to calculate the field due to each charge and add them together. The positive charge creates a field pointing away from it, while the negative charge creates a field pointing towards it. Let's denote the distance from the positive charge to P as our minus a, and the distance from the negative charge to P as our plus a. Using Coulomb's law, the field due to the positive charge is k times q divided by our minus a squared. Similarly, the field due to the negative charge is k times minus q divided by our plus a squared. When we add these fields according to the principle of superposition, and utilize the fact that for a short dipole is much smaller than r, we get that the electric field at an axial point simplifies to E axial equals k times 2 times p divided by r cubed, where p is the dipole moment. This field points in the direction of the dipole moment. Now, let's find the electric field at a point P on the equatorial plane, which is perpendicular to the dipole moment. Just like before, we calculate the field due to each charge and add them using the principle of superposition. Both charges are at the same distance r prime from the equatorial point, which can be calculated using the Pythagorean theorem as square root of r squared plus a squared. The fields due to both charges have components parallel and perpendicular to the equator. The parallel components cancel each other out, while the perpendicular components add up. After simplification, and for a short dipole, where r is much less than r, the electric field at an equatorial point becomes E equatorial equals k times p divided by r cubed. This field points opposite to the dipole moment direction. Now that we understand the electric field at axial and equatorial points, let's find the electric field at any arbitrary point in space. Using vector analysis and the principle of superposition, we can express the electric field due to a short electric dipole at any point as E equals k times the quantity 3 r dot p times r hat minus p, all divided by r cubed, where r hat is the unit vector from the center of the dipole to the point. P is the dipole moment vector, and r is the distance from the dipole center. In spherical coordinates, with theta as the angle between the dipole moment and the position vector, r, the magnitude of the electric field becomes E equals k times p divided by r cubed times the square root of 3 cos squared theta plus 1. Let's visualize the electric field pattern around a short electric dipole. The field lines emerge from the positive charge and enter the negative charge, forming a distinctive pattern. The field is strongest near the charges and along the axial line, and weakens with distance according to the inverse cube law. The formulas we derived for axial and equatorial points are actually special cases of the general formula. For axial points, theta is 0 or 180 degrees, giving us E equals 2 kp over r cubed. For equatorial points, theta is 90 degrees, giving us E equals kp over r cubed. Electric dipoles play an important role in many areas of physics and chemistry, from understanding molecular structures and polarization to designing antennas and other electromagnetic devices. Let's summarize what we've learned about the electric field due to a short electric dipole. The key points to remember are: first, a short electric dipole consists of two equal and opposite charges separated by a small distance compared to the field point distance. Second, the dipole moment P equals q times 2a, pointing from the negative to the positive charge. Third, the electric field at any point depends on both the distance r and the angle theta between the dipole moment and the position vector. Fourth, the field falls off with the inverse cube of distance, unlike point charges which fall off with the inverse square of distance. And lastly, we have specific formulas for axial points, equatorial points, and any general point. Thank you for watching. I hope this helps you understand the electric field due to a short electric dipole.